Hi everyone, I'm Achalesh Pandey. So I lead AI and digital transformation in GE Digital with over 20 years experience in the AI as well as digital as well as energy sector essentially. If you can go to next slide, please. So today what I'm going to do, I'm going to cover primarily on the grid side. Specifically, all the speakers have provided great details and insights what's going on in the energy sector, specifically with the distributed energy resources, renewable resources, how it is impacting the overall electric power grid, as well as the complete ecosystem. So I will focus on the electric power grid side, specifically the impact of the renewables and the distributed energy resources, like because it is the fundamental biggest problem of our time right now, this energy transition, whatever is going on, and primarily driven by decarbonization effort. Decarbonization is driving a lot of electrification, whether it is transportation sector or it is heat pumps or many other industrial side also. We are trying to move away from carbon essentially. So as we can see, EV demand that is coming from BNF electric vehicle outlook, 5,500 terawatt hours basically by 2050, the growth electricity demand from the EV is going to grow. And similarly, the increase in the renewable capacity by 2050 around 5,100 terawatt hours. So there will be huge amount of the growth in wind energy, solar energy, both, and as well as a lot of energy storage will be required to maintain and manage the grid because of the intermittent nature of some of these renewable resources here. As far as GE is concerned, I think we produce the GE equipments, our supplied equipments are producing 1/3 of the power of the world, basically. And we are moving around 40% of the electricity, electrons are moving because of the GE grid software, specifically here. And if you look into the energy transformation, so one is the conventional power sources, bulk generation sources like your gas turbines. Like it is definitely the number one thing right now to reduce the emission from coal to by applying gas, you can reduce 2/3 of the emission can be removed immediately. And the part to decarbonization is going for the carbon capture, utilization and storage, and then moving to the hydrogen, basically that is going to decarbonize from the gas perspective to maintain the stability in the grid essentially. But the huge growth is going to happen in the offshore and onshore wind turbine side. So the focus is growing the renewable generation. And then finally, how to connect and manage more renewable and these distributed energy resources. Like speakers talked about demand response and other things. So how it is impacting the overall grid, because it is absolutely critical from energy security point of view, as well as resiliency and stability point of view. So if you can go to the next slide, please. So everybody talked about all the speakers, so I'm not going into a lot of details here, but renewable is driving most of the renewable resources. The grid is becoming more and more non-synchronous in the future. Like today, it is running in the grid following mode. In the future, it will be running in grid forming mode. It is intermittent in nature. It is very probabilistic in nature. Plus, it is causing a lot of inertia reduction in the grid because these are not the big mass. It is connected to the inverter. So that is the kind of the challenge which we are going to see in the grid from the stability resiliency point of view with the renewables. And then electrification is going to pose different kind of the challenges. It is improving, it is going to increase a lot of load, as well as this load is moving load. So I think we need some of the demand response, as well as some of these EVs are going to become energy source storage also whenever these things are not running, so they can participate in supplying the electricity during the peak time period, as well as the consume the electricity in the off peak time period. So it is very exciting to maintain the peak, basically saving point of view. As prosumer engagement is another big thing here, because it is not as one single consumption, like one-way flow. The electrons are flowing two-way flow. These are not only just electrons. Now there is going to be information flow also. So that is another critical thing which utilities has to take care. And then corporate goal, like every organization is moving toward zero carbon by 2050, and some organizations are even earlier than that. And it is scope 1 to scope 3, all these emissions it is creating a lot of uncertainty also for the corporates, essentially, how they are going to drive the blueprint of zero carbon, essentially. And then there is legislative, regulatory, and energy markets are also evolving. And these are not uniform. Like even every single state in US is different. Europe region is very, very different. So these markets are evolving very localized manner, essentially, but everybody is going towards zero carbon kind of energy. And then the lot of investment, like in the United States Infrastructure Job Act, it is going to cause a lot of innovations, as well as a lot of investment on the infrastructure, improving the infrastructure, grid infrastructure itself here. So because of these challenges, whether it is driven by market trends because of the decarbonization, renewable growth, electrification, regulation, I think our utilities are facing a lot of challenges. And I'm going to focus going forward on the DER side. For example, these are the PVs, storage, electric vehicles, demand response. So where do we start? How do we get there? I think everybody is trying to figure out that because of the uncertainty, whatever is available. How can I keep my grid safe, reliable, and secure, including and with DERs? Because there is a lot of these are very probabilistic in nature, not like a conventional centralized generation sources where pushing the button in some time frame you are able to generate the electricity, which is predetermined, essentially. Here things are fluctuating a lot. And how do I satisfy my customer and keep energy affordable? So these are the challenges and question utilities are finding out. If you can go to the next slide, please. So if you look into how we are going to orchestrate, like this is all about how you are orchestrating, connecting and orchestrating these distributed energy resources or renewable energy resources. So these are the following pain points which we need to address in the industry. Like first of all, these DERs needs to be connected to the grid, and there is a long queue of these connections in the utility office. Like these needs to be connected to these wires, whether it is in the distribution side, basically you need to connect it to those. But when you connect it, you can't connect it to the place which is already congested. Like if it is congested, then you are not able to utilize your DERs. Essentially, if you want to put your EV infrastructure in a place where already there is not sufficient amount of capacity available in those distribution line where you have to move the electrons, you cannot do it. So there are a lot of digital twins capabilities are required here, or we are using right now, where it basically does those kind of the assessment, basically whether you can connect these DERs or where to put this infrastructure, what is the optimal location where you need to put this, how to connect this infrastructure so that we don't have any problem in the grid from the quality of the power quality perspective, whether it is voltage or it is currents. It should be within certain limits, otherwise your equipments will damage. So that's the one aspect of that here. And there is a lot of denials we get because utilities are overwhelmed with these connection requests actually. So first, connecting these distributed energy resources because these are exponentially growing to the grid, how to do it. That's the first pain point. Second thing, visibility. Like many of those things are not like big power plant or big loads. Now, some of these things are not, net load is very different than the actual load because of the behind the meter. And then if one cloud cover comes, then things completely change very, very immediately. So how to get the situational awareness and visibility to these distributed resources, whatever, when it is available or how much load is there in different places and how to orchestrate that, it is very, very critical because these are all the behind the meter. It's not very easy. It is very complex in that sense. Like where are the DERs and what are they doing? Does control room planning know? Today, in fact, distribution and transmission are two in silos, and we need to bring these transmission and distribution together because transmission doesn't know what is going on the distribution. Earlier it was fine, but now a lot of generation is happening at the distribution side also. So these are the kind of the situational awareness and visibility is required in the real time. And then other aspect is the controls, like because these electrons are moving in the real time. So you need to continuously optimize, as well as you need to basically ensure that you are orchestrating these, either it is load related resources or generation related resources in real time, by ensuring the security constraint. Basically, the security constraint is you are not violating any voltage constraint, you are not violating any current constraint, thermal constraints, you are not overloading any circuit, for example. So how to do that in a scalable manner, essentially. So that's the another aspect. It is not just it is at the edge. A lot of things are happening in the real time, essentially. And then last thing is here intelligence here, like as the violation can happen, as I mentioned, and you have to do the planning properly. And whether it is contingency planning or it is the planning for the optimization purpose, so we need to have the intelligence in the system where we are looking into the forecasting, AI capabilities and other capabilities which are providing some behavioral information about the loads as well as generation, both as well as weather conditions. And then we are running these power flow analysis and other things, look ahead analysis, to understand how can we optimize so that we are minimizing the cost. At the same time, we are meeting all the customer needs. We are supplying the electricity with the most resiliency and reliability, essentially. So that's the aspect of the intelligence pain point here, as we can see with the DERs. And last thing is the delivering the value. Like these demand response programs and others are all the non-wire alternative solution, which can help tremendously in reducing the peak demand. And basically, so how can we get the value? Plus, some of those things like I think previous speakers talked about the FERC 2222 kind of the requirements where some of these resources are going to be dispatchable, but this market doesn't exist today. This is just evolving. Today, most of the market is in the wholesale market, bulk market, generation market, where the energy trading happens. But now a lot of DERs can also participate in that wholesale market. How this retail and distribute wholesale market is going to interact. So these are the new business models are going to evolve. New flexibility services will evolve. So that's another aspect here, uncertainty with the utilities. If you can go to the next slide, please. So now let's talk about like what is the tech stack of the digital twin looks like, and how this whole large ecosystem is evolving. This ecosystem can be at individual circuit level, or it can be at basically even at a state level if it is small. Even sometimes it is at the country level, region level. So these are very large, complex network. And now we are introducing a lot of other ecosystem in the behind the meter here. So top layer is your physical layer, where you have the transmission utility, basically generation, bulk generation, going electrons are flowing through transmission network, and that is going to up to the substation. And then the electricity in transition happen here because of the wholesale kind of the market, which are operated by RTOs, ISOs. And then from the substation, we are moving these electrons to the consumption sources through distribution utilities, basically. So these are distribution network. And finally, it is on the consumption sources. But these consumption sources are also becoming now generation sources. Like, so it is PV, or it is small wind, microgrids, EV charging, batteries, heat pumps, smart thermostats, microgrids. So you can name, like, there is big ecosystem is evolving. And that's what you see, that earlier in the past, this arrow was one directional, but arrow is two directional. It was only the electron basically was moving now. Now the information is also moving here. Some of the wholesale and retail market were independent. Now these things are also bidirectional today. So that's the physical layer at this, or the market layer at the top, where these things are happening. And below that, you have the application layer. And there will be n number of applications basically to meet different customer needs, different customer demands. For example, in the transmission side, GE has the product called Advanced Energy Management System. And the job there is to have the capability on the planning, monitoring, optimization, control, as well as managing these markets, clearing these markets, those kind of application. And digital twin is on the centerpiece of that. So the transmission energy management. Other big area here is distribution management, basically, which is primarily, as I mentioned, moving the electrons from substation through the distribution network to the consumption sources. And here you have to monitor, you have to do the switching, whole bunch of other things. And finally, it is the third application layer, and there will be suite of the application under that layer is your DER management system here. Basically, you are managing distributed energy resources here. And these applications can be divided into these 5 categories here. So first you have to do the planning. This planning horizon also changes. Like if you are building if you are bringing new these generation resources, these EV infrastructure or anything, it's not going to happen now, but you have to do the planning now because these infrastructure exist for very long time. These generation sources exist for 20, 30 years, like new wind turbines. If you want to install today, this is going to last for 25, 30 years. So the utilities as well as generation utilities have to plan for some of these resources. So you have to do the long-term planning for the investment point of view, and digital twin is required for that. Or you have to do the short-term planning like day-ahead planning, what is going to happen in 24 hours, how the weather will change, how the demand will change, how the supply is going to happen. And you have to do hour by hour and minute by minute kind of the planning also. So planning is one critical aspect of the applications here. Then monitoring is your situational awareness. As previous speaker talked about virtual sensors. Yeah, if you think about these, the number of sensors are limited, and you have to monitor the condition of these currents as well as these voltage and other power factor, all those things at every single node for orchestrating this grid. So you use a lot of power systems kind of the model that creates a lot of virtual sensors, and you have to do that. So to get the situational awareness in the real time, essentially, to know what is going on in different part of the grid. And then once you have the situational awareness, you want to optimize, you want to do the optimal power flow, you want to minimize your overall cost, or your optimization problem can be, hey, I want to maximize my revenue here by supplying some of the ancillary services or energy services which I have here. And then finally, the controlling here, because just planning is not going to get the actual outcome. So it is more action side here. In the real time, now you are doing either switching operations, real time you are managing your reactive power, you are managing the active power in the grid, or you are basically doing the demand response, like how much electricity we want to get from, or if there is any curtailment is required, how much curtailment I have to do. So all these things are through control layer at the edge, essentially in the real time. And then finally, transactive or market solution here. So once you have supplied the electricity, then you have to get monetization also. And here a lot of energy trading happens in the day ahead market as well as in the real time market, spot market. Plus in the future, as I mentioned, these retail market, these because of the FERC 2222 in US as well as other parts of the world like in the Europe and Australia and other places, this transactive energy market is going. It is very new right now, but that is also growing, that how basically DERs can participate in this kind of the market and make the money essentially. So that's another aspect here, as you can see. And below at the bottommost, there is the layer basically where we have the data and digital twin foundation. And this data can be, I have not listed here a lot of data sources. It can be scattered data that is coming in the real time, what's going into the grid, like your current, your voltage, your power factor, whatever you name it. Or this data set can be your weather information. This data set can be your vegetation information, because you have to maintain power lines without any risk of vegetation related outages, for example. So there are n number of data sources here at different time scale and dimension you need, from real time till it can be year kind of information is absolutely fine. Then you need the geospatial information, because electricity grid is basically very much spatial in nature. You can't just do the line diagram there, but you need the spatial information, because especially in this grid infrastructure is impacted by weather, climate change, so many other things. So to make the decision, you need the GIS information. You need the network model. Network model will include the asset information, like these are the conductors, what is the impedance level, all kind of the details are here. And the physics model is basically giving you the physics-based digital twin virtual sensors here. These are the power system model, which is solving very complex Kirchhoff's law kind of the problems here. And then state estimator, that is another tech stack you need, basically because some of these models are for that design-based models. But you need to basically personalize these models, tune those models so that digital twin definition is synchronized to the current state. So that's what you need the state estimators here. These state estimator can be Kalman filter, particle filter, unscented Kalman filter, all those kind of things. Or some of these things are AI based here. And then forecasting engine, it is giving you the behavior of the generation as well as load forecasting, as well as weather related forecasting. And finally, if you want to predict the inertia, for example, or you want to predict other parameters, so AI will play a critical role. I think currently the control systems or optimization we are doing with the traditional methods, but in the future it can be augmented by reinforcement learning kind of the solution. I think our previous speakers talked about that. Basically, so this AI is going to play a significant role because of the diverse data sources. Not only this is going to play the role only on the prediction side or optimization control side, but how to even figure out these data qualities and filling the missing data gaps or basically getting the contextual information. So AI is going to play a significant role there. And then optimization, and then at the top of that, essentially to drive basically optimization at the top of all these predictions, whatever we are making. So essentially, this whole digital twin will play very, very critical, significant role to enable reliability, resiliency, and affordability of the future grid here, essentially. So where is the future? What are the technology challenges we have to solve for the future of grid? Like if you look into building an accurate digital twin of the network with large scale renewable and DERs, which we are getting into the grid, because even these power systems model these DERs are exploding. There is no visibility what is going on in the behind the meter side. So even how you will even come out with the accurate data related to that, accurate network model related to that. So that's the big challenge which we have to solve here. And then second thing is here operating the grid with the renewable penetration is happening here. It is becoming deterministic to probabilistic. Today, all the most of the analysis we do in the power systems model and other, because of the criticality of this, is the electricity is very critical for everyone. We have to ensure the resiliency. So everything is deterministic in nature, but it is going to be probabilistic given the kind of the things we see because of the weather and intermittent generation sources and load profile changes and other things. And then how to maintain the grid stability with the low inertia grid, because more and more DERs and renewable generation is going to make the grid and reduce the inertia in the grid. So how to maintain the inertia how to maintain the stability with the low inertia? You need very, very flexible, fast balancing control, like which we assume today are given because of these big mass of the generation sources, like big plants there. But in the future, it is all inverter driven thing. So this can be at the millisecond level to few seconds level, kind of the response we are talking about here. And how you will track the millions of the electric vehicles and leverage that for grid reliability and resiliency essentially. And then these markets are evolving. How you are modernizing the energy markets, the business models which are changing, that's another big problem needs to be solved here. And because now the grid is becoming more and more, we are connecting to, it will be connected to the cloud, and we are now connecting EVs or buildings, all kind of the things on the grid. And the communication, this is not just electrons are flowing, but there is information is also flowing there. It is connected to internet. So how to protect for that cybersecurity, that is going to be very critical for the adoption even on the cloud and other side here. And then leverage AI and ML because of this tool which we have, how to leverage it, because all problem cannot be solved with the AI and ML. To how to solve that, to maintain this lot of data which we are collecting, and then lot of problems, optimization problem will become very complex and probabilistic. So AI and machine learning kind of the tools can help here, capability can help here to optimize the grid for tomorrow, from going from reactive to more proactive in the nature here.